So today we will start the shortest path problem, and this is due to the Dijkstra's. Okay. And while he was taking Nescafe with his wife, then he was taking the decision that probably that from that place how to reach the another place in less amount of time. So at that time, she discovered the he discovered designed this algorithm and became famous. And it took, I think, if I'm not wrong, within 15 minutes he designed the algorithm and he proved the correctness, everything. Okay, and he is a Turing Award recipient. Probably you know. Anyway, so what is the problem? Given a weighted graph. Weighted graph means the distance between the cities are denoted by some weights. For example, you see this is a weighted graph A, B, C, D, E. Okay, so these are there are some weights on each edge which represents the distance between two cities, say A and D, or it may be the time required to reach from one city to another city. It may be anything. So theoretically, these are the weights on the edges. So this is called weighted graph. Now, G, this is a weighted graph. Okay, there is a weights on each edge, and all the weights are positive. We are taking in this case positive. So the length of the path. What do you mean by length of the path? So weights are denoted by WUV or WE, where E is the edge that connects two vertex U and P. Now the length of the path that starts from V0, V1 is the sum of the weights of its constituent edges. Okay, so that means you go like this. So weight of this edge, weight of this edge, weight of this edge. You add all this to find out the path length from U to V. Okay, in between say W, there is another X. So this is the path length P. So this you add all the weights on this 8, 2, 3 like this, then you will get the length of the path. And the distance from U to V denoted by delta UV is the length of the minimum length path. There may be so many paths. You see from A to C. From A to C you can go via this or you can go via this. Clear? So which path gives you the minimum distance between A and C? That is called the minimum path length. Okay. So if there is a path from U to V, that is called minimum distance. Otherwise, it is made infinite. Means if there are no paths. So length of A, B, C, E is 6. So A to E is 6. You check A to B, B to C, C to E. So 2 plus 1 plus 1. This. Okay. So this gives path length 6. So now you have been given a large graph, and you need to find out the minimum path length from one source to all the destinations. So how it can be done? So using this algorithm, single source shortest path by the Dijkstra's. Now formally the graph are positive. Please remember it will not work with negative edges. So you will be able to see why it does not work with negative edges. So for given a graph with positive edges and a distinguished source vertex is there, S. And we need to find out the distance and the shortest path, means the path through which it goes. The path from the source vertex to every vertex in the diagram. Diagram means directed graph. The graph has direction. Now here
sir, could you repeat the question once more, sir? I'm sorry I missed out on that. So could you repeat the question once more?
Which one?
Diagram? Sir, yes, sir. Diagram, sir.
Diagram is directed graph. There is a direction. From A to B there may be a direction. Means if it is like this, you can reach from A to B. Okay, but not from B to A.
Okay, sir.
Okay, that is directed. Undirected means both way. Single source shortest path is any subpath of a shortest path. Any subpath of a shortest path must also be a shortest path. Okay. Any subpath of a shortest path must also be a shortest path. Yes, it is true. You see, just I am telling this. Suppose this is the shortest path, okay, from A to say B. Now, in this case, say this is G and this is H. So G to H, this path will also be the shortest path from G to H. If you say no, it is not shortest path, there are some other shortest path from G to H, say like this, maybe you are saying, claiming, okay, fine. If you will say that this is the shortest path from G to H, then I will say no, then A to B, the shortest path will be along this. Is it clear? The proof is very simple. Because then I should follow this path. If G to H is, this is the shortest path, then I will go from A to G, then I will follow G to H shortest path, then H to B. So that means this will not be the shortest path, but you are saying that this is the shortest path. So that means if any A to B is the shortest path between A to B, then any the subpath that subpath means that the two vertices that lines along this path, say G and H, or suppose this is I and H, so this will be the shortest path. Now, report all the vertices in the increasing order of their distance from the source vertex. There will be a source vertex. You will be given a source vertex. From that vertex, you need to compute the distance of all other vertices from in the graph. So, now construct the shortest path tree. Shortest path tree means it goes from this to this, then this to this, then this to this, in this way. Okay, you are generating from the sources, and you are this tree is growing. So you construct the shortest path tree edge by edge. At each step, adding one new edge. You add a new edge. This is the tree. Okay, you are adding the edges like this, and here suppose this is a partially constructed tree. Then you will add next edge. Suppose I am adding this next edge. So I am adding this edge, but there is a mutation. I cannot randomly add this edge between two these trees. Someone may add these two. So why I am doing this? There should be some reason. So at each step we are adding one new edge corresponding to construction of the shortest path to the current vertex. So there is some rule. So what is the rough idea of the discrete Dijkstra's algorithm? So we will maintain an estimate distance dv, okay, dv to the of the length delta sv, okay, delta sv of the shortest path from each vertex. So delta is, you please remember, delta means exactly shortest path, exact value of shortest path from S to V, and we are taking the help of dv. What is dv? dv means the distance from S to V, and we will update it. Means we will initially it will be very large. Then I will change it, minimizes as the tree grows. Then I will update it so that finally dv becomes the delta SV. So that's why dv is estimate, not the minimum distance, minimum path length from S to V. But finally we will make it equal to delta SV, that we need to compute. So that means always what happens, dv is greater than equal to delta SV, and dv equals the length of a known path. So if there is no path from S to V initial sub, so then we will make it infinity if we have no path so far. So initially what happens? Initially ds is 0. What do you mean by ds? ds means from S to S. This is the a source. So from source to source, this distance is 0. So that is 0. And from source to all other node distance of all other remaining vertices is infinite. That means this is the first step. Then I will change it. Okay, initial. This is the initialize. Okay, so initially the distance of S to all other nodes are infinity. That's why dv is infinity for all other values. And then the algorithm will process the vertices one by one in some order. There should be some order. in which we should process the vertices. That will be clear when you will read the algorithm. So the process vertices estimate will be validated as being real shortest distance. That means whenever you are adding, suppose these are the set of vertices. Okay, there is a small set S. Now whenever you are adding V, then what will happen? These V you will add so that dV, this is the dV becomes actually delta S comma V, and you have to update something. So here processing a vertex U means finding a new path and updating dV for all V that are adjacent to U. Okay, if necessary. The process by which an estimate is updated is called relaxation. Relaxation term is used to tell that this is the process by which we update the estimated values. Now when all the vertices has been processed, we will see that dV will be the shortest path from source station S to destination station V for all V. Now there are some questions. Then how does the algorithm find the new path and how do we relax? Similarly, in which order the algorithm process the vertices one by one? So that will be discussed in the algorithm. See, what happens when first question you check how does the algorithm find the new path and do the relaxation. So when processing a vertex U, suppose you are processing a vertex U. This is the vertex U. Now it has some adjacent vertices. These are the adjacent vertices of U. So what we will do, when you are processing a vertex U, the algorithm will examine all the vertices V, where V belongs to adjacent. Means this one may be V, this one may be V, this one may be V. Okay. Now for each such vertex V that are adjacent to U, a new path from S, this is the S, somewhere I am drawing this curvilinear means there are so many other vertices. This is S. So I will update the path from S to V. Okay, path from S to U plus new edge. S to U plus new edge. That means I am coming from here to here, and say from this to I am going to this. There are some rules that we will see. And relaxation, if new path from S to V, say this is the V. Initially, suppose there were some other paths that we took. Suppose it was 25. Now when I am discovering U, okay, when I am processing the vertex U, then I am saying if I go follow this path, if I follow this path, then I am reaching V at distance say 15. Then automatically I will reject this path. I will not take this path. I will update this path. Update this path means I will tell that okay, dV means distance of the vertex V from the S is 15, not 25. I will take this. Okay, so a new path from S to V is found, and path from S to U plus new edge. If the new path from S to V is shorter than dV, then update dV to the length of the new path. That I have told. If I see in this step that the distance of an adjacent vertex of U becomes minimized, then the existing distance of V from S, then I will update it. That is called relaxation. So whenever we set dV to the finite value, there exists a path of that length. So therefore, always delta V, dV, you see what I am doing. We are trying to minimize the distance of vertex V from S always at each and every step. So that means dV always should be greater than equal to the exact minimum path length from S to V, means delta SB. So whenever they becomes equal, then no more relaxations are required for that vertex. Now,
sir, could you explain again, sir? I'm a bit, I didn't get
it will be explained through example.
Okay, sir.
Now, how can we implement? So consider an edge from a vertex u to v whose weight is w u v. Okay, u to v. Now suppose that we have already processed u, so that we know that du is this, and also computed the current estimate of dv. dv is the distance. Please remember, dv means distance from S to V. It is not exact minimum path length. Exact minimum path length is this delta SB, that we have not computed. Whenever these two values becomes equal, then we will not update dv. That I am saying in the previous slide. That I will update this. Whenever you will see the example, it will be more clear. So here you see there is a shortest path from S to U with length du, and there is a path from S to V with length dv. Clear? Now combining this path to form S to U with edge uv, and then another path from S to V with du plus this, means you see the figure. See what I am doing. I am saying that this is the vertex V. I have already a path to V, from S to V, this one. Okay, this one. That is dv. Now I am exploring U. Now, right now I am exploring U. Now I am seeing the one of the V is the one of the adjacent vertex of U, and this is the weight of U to V. U to V. Now I know that this is the du. How much time it takes to reach from S to U? This is the time, means this is the path length. This is the du. Okay, if I add all this, I will get du. Say suppose this is 268. So du is 268, 16. Clear? Is it clear? Tell me what I am saying du. Now suppose this is 4, and suppose this path length dv is already computed is 30, means say it may be 10, it may be say 12, this is say 8, and this is 10. So this is 30. Now you see it is already computed, dv is already computed. Now I am at this moment, suppose I am exploring U. I am checking, okay, V is the shortest path, V is the adjacent vertex to U, and this is the 4, weight of this edge is 4. So and therefore if I can reach from S to V via this path also. So what will be the weight path length of this? That will be the du, means 16 plus w of U to V. U to V weight 4. So 16 plus 4 is 20. So 20 is less than 30. Check it. So that is a, if du plus omega of uv is less than duv, then what I will do? I will replace the old path, means s to omega to v. This is the s, this is the omega to v, with the new shorter path s to uv. That means this is a. I will take this one. That this is the u, and this is the v. So what will be the dv? I have to update this dv value also. So this will not be 30 now. This should be 16 plus 4, 20. So that du plus only this 16 plus 4 is 20. Is it clear? Tell me. Hello.
Sir, I think the example will be easier to understand.
No, example will be easier. I know. What I am saying. This is a partial step that I have already computed S to V. Suppose at
Yes,
that
sir.
time U was not explored. U was not explored. This path was not explored. Clear? Now I have 30. Now when I am see, please remember that tree. This is a tree. You check it. S to this path is a tree. Okay, except the red one. So whenever I am constructing the tree one by one by adding an edge. So what happens when I am reaching to U, then its distance is 16 from S to U. Now I am checking that there is a path from U to V. direct edge. So if I add that, then I will go from U to V by an weight 4. So what will be the total weight from S to V if I follow this path? Tell me. What will be the path length? I have written all the edge length. Check it. Tell me. 2 plus 6 plus 8 plus this edge. How much?
20.
20. Now 20 is less than the previously computed shortest path, dV. So I will ignore the previous one. I will update this. That you do, na? That you are following. Suppose from say hall 4 to you are following a path from hall 4 to your classroom. Now in next day, if you see that there is another shortest path, then you will update that. You will not follow the previous path. That this is the same thing here we are doing. It was unknown. That's why you are not following, but it is not known that you may get benefit. That's why you are doing that. And in that case, through which vertex you will follow? Means what will be the previous vertex of V, U or W? Tell me if you update. If you update the path, then which vertex will be the previous vertex of V in the updated vertex, the updated path? U or W? Tell me.
U.
U. So that's why now preceding vertex of V will be U. This is required. Why? This will help you to find out the path, not only the weight. You are not only interested in the weight of the path, but you are also interested in the path along which you should visit. So originally it was this. So that is called relaxation that we are doing. Relaxation between the two edges UV. You check if distance of U is this was du. Okay, if du plus omega of u comma v, and this is dv. So it was originally computed dv. Okay, this dv. So old dv. If it was larger than du plus dv, then I will update this dv as the new value of du plus omega. And I have already said that this array will be used for determining the shortest path. Now, what you will do? Dijkstra's algorithm operates by maintaining a subset of vertices S. B is a set of vertices S, or that means initially S is single small s. Okay, then you know suppose S2 that vertex. Fine, you have computed. So these will be the S. Now you have added another edge, this another vertex. So these will be the S. In this way, the set S increases, and the V is a whole set of vertices. Clear? So for this set of vertices, capital S, I know the minimum distance from small s, the source vertex, to all other vertices that belong within this. Now initially S is phi, empty set, and ds is 0. Okay, there are no vertices in this. Now, and dv is infinite for all other vertices. This is the initial value. Now, one by one we select the vertices from v minus s. V minus s, this is a set of vertices. Okay, v. So you are adding one vertex from to this s. So v minus s, v minus. So you are adding from set of vertices v and you are to s. The set s can be implemented by an array colors that you will see. Color, you make a flag. So color will be black, means it has been processed. White means it has not been processed. Okay, means black means yes. I will show you the algorithm, a figure. Okay, just but before that you should know the property what we are doing. Now, what is the next question? There was a question in which order the vertices should be processed. In which order the vertices should be processed. So the best order in which to process the vertices so that estimates are guaranteed to converge to the true distance. Okay, so the algorithm select which vertex. Algorithm select which vertex. See, there are a set, there is a set, say this is the V, and you are selecting so many vertices from it. Now you are suppose selecting this, on which or property or on which observation, what is the observation based on which you are selecting this? This is the question. So answer is that is a greedy algorithm. This is one. For each vertex U that belongs to V minus S, we have computed a distance estimate du. The next vertex, so I have a set of vertices from this. Means I have computed du values for all these du. What are the u? These are all u. Now, which one is the minimum? I will take that one. Okay, I will take that one for which du value is minimum. And I will add it to the which? This set of vertices S. Like this. I am adding. Therefore, I will add this in this way. But automatically there will be a question that what is the guarantee that you will get minimum? Greedy is always easy to design but difficult to prove. So how do you implement this efficiently? So basically this you maintain a priority queue. You know that heap is used to priority queue, where heap is a complete binary tree and you can fetch, means insert or minimum value, decrease, everything can be done in log big O of log n time. So I am not going to that. That there are some operation insert. Insert means you insert a in the key value in queue. There is a priority queue, capital Q, and you extract operation, extract minimum, extract the item with minimum key value, and decrease key, decrease the use key value to the new key. These are the operations, and this is the algorithm. Okay, this is the algorithm, and the next I will show you the example. So I request you to check it. Very important. Dijkstra's algorithm, because you are reading the algorithm, means who is the Turing recipient award. Really, this is a very simple algorithm, but means I am saying based on his algorithm, there are so many PhD thesis has been covered also for others. This is now means it was updated. Negative values means it cannot handle the negative edge. There are so many other things. Anyway, so Dijkstra's G is the graph, W weighted graph. What do you mean by S? S is the single source vertex from which you will start. Now for each vertex U in V, what you will do? du is infinite. I am assuming that there are no paths from source S. So that's why their weights are infinite and all these are colored white. Now ds is 0. Distance from S to S is 0. Fine. And predecessor of S is nil. There are no predecessor vertex from S because this is a single vertex. Now Q, what is Q? Priority Q. Q of all the vertices. Q of all the vertices means what? See, you know the priority Q has a priority value. So which is the priority value? du. That we will use that du value. Okay. Now while the Q is not empty, we have to do something. What? I will find out that next minimum vertex based on du value. du. All the vertices has du value. So extract minimum. Now for each vertex V, so you have chosen a vertex U. Fine. Now it has adjacent vertices. Say these are the adjacent of U. I am saying these all as V. So for each V that belongs to adjacent of U, if distance of U, if dV is less than du plus omega of U to V, you check. If du plus WUV is less than dV, then you update it, means you change the dV value. dV will be this du plus omega of UV and decrease the value of the priority Q. Okay, and you take a predecessor as the U. You will follow this and you make the color of the vertex U as the black. So in this way you process all this until the queue becomes empty. Now come to the example. Check it. I think just a minute. It will be better if I show using another just. Yeah. Can you see here example? Tell me. Hello? Is it visible?
Yes, sir.
See this example. This is the source. You please check it clearly. Then it will be everything will be cleared. Here. Sorry. You see? I'm just using the mouse. This is the S. Is it clear? And this is the A, B, C, D. So step 0 is the initialization. You check it. S, A, B, C, D. 5 vertices, set of V. Fine. Now what are the DV values? Only these has D, V is 0. All are infinite. Check it. What are the preceding value of the vertex? All are nil. What are the colors of the vertices? All are white. What is the priority queue? Priority queue, you see, these are the vertices, and the priority queue, you see, this is the 0, and these are infinite. So at the top of the root of the priority queue means heap will contain this S. Fine. Is it clear? First step. Now, so in this case, I will make S. S is the minimum. So I will select S, and S will be black. Clear? Now check. Whenever I am selecting S, it has 2 adjacent. How many adjacents? 2 adjacent. What are those? Tell me from the figure. Which vertices?
Sir, 2 and 7.
Don't say 2 and 7. A and B.
Sorry, A and B, sir. Yes, sir.
Okay. Now A and B. Fine. Now tell me what is the edge length? Means from S to A. 2. S to B 7. That's why DV. This is the DV, distance from S to A and S to B. Check it. 2 and 7. I am not saying this is the minimum. Please remember, this is not the minimum. But at this moment, this is the minimum. Means at this moment, I can reach to this. Okay. And what is the preceding vertices? C cannot be reached. C cannot be reached from S, from direct edge. So that's why they are remaining infinite. And what is the preceding vertices of A? S, B, S. Check it. And color of the S will be made black. All other remains white. And priority queue, you see what becomes the priority queue? 2, 7, infinity, infinity. Automatically 2 will be at the front because it has minimum. Now tell me which one will be selected? I told that the vertex whose DU value is minimum will be selected. So which node will be selected now?
Sorry.
A. Fine. Check it. So after this, here, I told you that there are 2 sets, capital V and capital S. Capital V is the set of all the vertices, and capital S is the vertices that you are adding. So what is S now? Capital S? Tell me. At this step, when you are selecting 2 also, vertex A also, what are the S? Capital S? Set of vertices which are black?
So 0 and 2.
Not no, S and A.
Sorry, S and A. Okay,
S and A. That are the D values. Na? So Anyway, now here actually I cannot annotate this PDF now because I have used something different software. So here you see this is the, you check it. This is the set of vertices, means is capital S. Now what are the adjacents to this? See, B is already adjacent. C is also adjacent.
Said D also.
D is also adjacent. Now, see, in this case, for example, you try to remember, initially it has B had 7, check it, B had 7 because this was edge. Now, whenever you are adding 2 also in this set, what is the path length, means dB value? See, there is an edge from this to this, check it, from this to this. What is the weight of that edge? Weight of edge from A to B, tell me.
So 3.
Sir, 3.
3. And what was the D value of A? 2. Is it clear? So 2 plus, means D2, DA plus WA to B. That means 2 plus 3. So if I go through this, this will be 2 plus 3, means 5. And what was this length? DB? 7. So which one is larger? Previous value or now listen this value? Tell me. Project, tell me.
Sir, this value, sir, this value. So 7 is greater, sir.
Greater than. So I need to update it.
Yes, sir.
So what I will do? I will DB as the 2 plus 3, 5. So check it. This or B entry. Check it. It is 5 now. But before that it was 7. So I am using the relaxation. Okay. Is it clear now?
Yes, sir.
Yes.
Now for C it was infinite. You check. Before that it was infinite. Now whenever I am adding this, what happens? This 2 plus 8 means this. You check only DA value and this 8. So 2 plus 8 is 10. And this 2 plus 5 is 7. So I have updated. And what is the preceding value of the vertex B? A. Preceding value, so C is A, D is A. And I have made this is the black. Clear? So now among these white, I will create the priority queue, means update the priority queue. So which one will be the minimum? This 5. So in next stage, which vertex will be chosen? Tell me. Which vertex will be chosen? Tell me which vertex will be chosen. I told you that I should use that vertex for which the DV value is minimum. So tell me which value, which vertex will be selected, B or C or D?
Sir, B.
B.
So next B. Now whenever you are adding, you check it. This, then you see the C value is updated, is DC value. Because you see, initially it had 10. 2 plus 8. 2 plus 8 was 10. Now after this, please mute. 2 plus 3, 5. And this 1, 6. You check it. This is the entire set of vertices, S, capital S. This 3. So C is the now adjacent of B also, not only A. So I need to check whether I can update it or not. See here, 2 plus 3 value was 5 B. So 5 plus 1, 6. So it is updated 6. Is it clear now?
Yes, sir.
And then I am updating the preceding vertex also, B. And you check which one is the minimum among these two. C is the minimum. So next I will choose C. And in this way, I am updating. Priority queue becomes empty, so we are done. You tell me, is there any confusion?
No, sir.
So in this way, you need to compute. And you see the order in which we added, you check it. For example, if anybody asks, see this is the, you see this table is showing shown again in the next page, that color part is all the colors are black, fine. So we are not considering this, but you check only V, DB and preceding. Okay, these values. So if anybody asks you that what is the shortest path of from S to D, you check it, it is value is 7. And what is the path information? So how can I get path information? You see here, D, what is the preceding vertex? A. So D to A. What is the preceding vertex of A? A's preceding is S. So that means S. So S, A, D. 2 plus 5, 7. Clear? Now if anybody asks what is the shortest path from S to C? Okay, C. So check the matrix. C shortest path is 6. Fine. What is the path? Path information. See, path is, okay, preceding vertex is B. Okay, so go to B column, B. Preceding vertex is A. Go to A, preceding vertex is S. So that means C is preceding, so take it C, B, A, S. So that means you can, once you compute, then you can retrieve the path through which you should follow to reach the destination from S. Is it clear?
Yes, sir.
So this is the tree. You see why it is called shortest path tree? You check, there are no cycle. There are no cycle. Now for correctness, I am just showing another one here, because this contains better. You can see that they have used this is the source, and here you see this was S that I was saying. This is the set S. Check it, this set, and from this say this is the minimum, means this is the adjacent, this one is also adjacent, this one is also adjacent. You compute the D values of all this. Which one is minimum? You select, you will select that you know already. Okay, so you are taking that as a pi v. In this they have taken as a pi v. In means which one is the minimum of du plus le? See, you are checking the du plus le means edge length, edge from this to this. You see, you are adding this S is increased. So for each node u, du is the shortest length. Du is the shortest length of shortest path from S to U. I have to prove. Okay, by induction. If there is only one node, fine, trivial, assume, is basic case, base case. Induction hypothesis, you assume that if the set consists of k vertices, S, if S, this S has k vertices, then it is true. Okay, that du is the shortest path from the, all have the du value, na? So dx, du, all have. So these are the shortest path from S to this. I am assuming. Now let V be the next vertex, this one. V be the next node added to S. By Dijkstra's algorithm, we are adding V. Why we are adding V? Because dV is the minimum among all other nodes. From V minus S. You can write in this way also. Okay, V minus S. This is a set of nodes, and these are the from V minus S, that Y, V, and others are also there. Now from that we are choosing V. So V is the next node added to S, and let UV be the chosen edge. I am choosing this edge. Okay. The shortest path S to U S to U is the shortest SU path plus UV, U to V is the shortest length pi V. We are claiming this pi V. Okay. Now you are saying no, this is not the shortest path. This is not the shortest path. Dijkstra is calculating this as the shortest path from S to V, and you are saying no, this is not the shortest path to V. There are maybe some other path like this which gives me the shortest value of the path from S to V. Means this. We are telling that path as the P. So okay, so this S to V path is the P. You are saying that this is the shortest path. Okay, I am assuming you are correct. Fine. Now I will show you that you are wrong by proving this that it will be less than this. So how? So suppose, see, if P is a path that you are saying which goes from S to finally V through some nodes, and I am sure that this path must exit the set S. What is the set S? This set of nodes S, this gray colored. Okay, so it will cross the boundary for the first time because V is outside. So to reach the V, this path must cross the boundary for the first time at least once. Here it has been shown 1, 2, 3. It may be 4, 5, or it may be at least once it will exit this. So this X to Y. So let XY be the first stage in P that leaves S, and P prime be the subpath to X. What is the P prime? We check. This is the P prime. And this is from this to this. P prime. So I know P prime is inside this S. Okay. That means K S means it is correct. DX value. Now P is also when P is leaving the path P. You see which one is the path P? This. Please show. You see I am showing using this mouse. This is the entire path P. So this length of this path is greater than equal to length of this path P prime plus the edge X to Y. You check it. I am saying this portion. This is the length of the path P prime plus L of XY. Length of path P. Is it clear? Yes or no? Tell me. Length of this entire path is greater than length of up to X and then X to Y. Hello?
Sir.
Is it clear to you or not? I am asking. That I am saying this is the path P. This path P is greater than this to this and this edge. Is it not so? I am asking.
Yes, sir. Yes, sir.
So then why are you silent? So length of this path is greater than this plus X to Y. It may be equal when Y is V. If Y and V are same, then it can be equal. Fine. Now you see, this length of path is greater than equal to dx plus lxy, because you see I have a shortest path from S to X whose value is dx. I know. So L now this path L of P prime must be greater than equal to dx. So just I am doing that. Plus lxy. And I know that by definition this must be greater than equal to pi y. What is the pi y? Pi y is the shortest path from S to Y. Shortest path from S to Y, that I do not know. Then it may be like this. It may be like this. I do not know. But I know that if that was any shortest path exists from S to Y, so then this dx plus lxy, either it will be the shortest path or it will be greater than the shortest path. So that means this path will be greater than equal to pi y. Pi y is the shortest path. They have used here pi y, shortest path information. Okay, means that value. And this pi y is greater than equal to pi v. Why? Because Dijkstra is choosing this one as the next node. Means from v minus s, he is choosing v this node because its d value is minimum. So means pi. So therefore pi y is greater than pi v. So therefore the length of the path p is greater than equal to. So if it is so means it is true for all the other cases also. Here also proof is shown, but I think that proof means the language is very easy within a slide. That's why I have shown you. Otherwise you can see this is also same thing. Okay, same thing. Nothing different. Analysis part is also very easy. You just check it. Okay. See what you are doing. Actually, you have to go see the algorithm first again. The code. You see, please, this one. I am just minimizing slightly. Yeah. For this, so how can you store infinite values? Tell me.
Sir, could you repeat the question, sir?
I am asking that here. Just I forgot. I was how many means how many nodes are there? No, sorry, not how many nodes are n nodes are there. How can you store the infinite values to du initialize?
Sir, max int.
Right. Who is it?
Sir, Vikas Kumar.
Okay. I do not know the face. I have to guess. Anyway, thank you. You store the maximum value of integer. That can be, I can say, or 65535, or say long int. Okay. So that you take as the infinite for implementation purpose. Now here you check that you are doing this for all the values of. It's not annotated. Again, it's creating problem. Anyway, so this is, you see, the for each u value you are assigning infinite and color is white. Then these are the constant time. Then you are creating this queue with all the vertices in log n that you know. And then while not queue empty, then you are doing extract minimum. And for each v adjacent to this, that means even vertex u has e number of adjacent edges. Then for those many edges, you have to do these operations. And here extract minimum, it takes log n operations. Okay, it's big of log n. So these will be these are the main steps. So check it, the time complexity part. Yeah, this thing. You are checking non-empty, called one for each vertex in terms whether it is not empty or not. Extract minimum. Okay, and for each inner loops, that for each edge v to adjacent of u, you are calling, and if there are m edges, okay, then it takes big O of m times. If there are m, so constant time plus decrease key operation. So, and you know the priority queue operation requires big O of log n, where n is the total number of nodes I'm assuming. So the total time complexity will be this n into this, you check it, that will be n plus e log n. You are using, I am saying you are using here, please remember, how can you represent the graph? Adjacency? Data structure, you know, I think. Tell me.
Sir,
Hello? Adjacency matrix and adjacency list. Hello? Hello? I do not know. Okay. Can you listen to me? You check, I have uploaded all the slides also about the graph, basic graph theories. You should know this. Anyway, there you will also get. So adjacency list is used. So therefore, you will get this big O of n plus e log n. And you please read, I think